All right. So, in today's class, I'm going to wind up the entire transformer architecture. As you are seeing right now, this is what we have studied, the transformer, which is having two components, encoder and the decoder. The task of encoder is to take the input, convert it into embeddings, give to the attention mechanism, perform feed forward, and produce the output which will be given to the decoder. Decoder do have multi-head attention, two multi-head attention. One is masked and one is encoder decoder multi-head attention. The task of the decoder is to produce the output. In general, the transformer architecture was built to perform machine translation. Later on, it's been used for a variety of purposes. Okay, so I will give you now the re explanation of what we have studied in the previous classes. You have to listen carefully. So, as I said, transformer is having two components, encoder and decoder. Obviously, they are neural network. Transformer itself is a neural network. If we talk about encoder, it is having three components: positional encoding, multi head attention, feed forward network. So, when you give text as an input to the encoder, it first create tokens. It do perform vocab, that is the integer annotation of the tokens. Then it convert them into word embeddings. That is the vectorization or vectors. Okay. Then it add position embedding to it. That is also a vector. This whole task comes under positional okay. So, for example, if take a word the word embedding of the is 0.1, 0.2, 0.3, 0.4. Let us suppose the positional embedding of word the is 0.01, 0.02, 0.03, 0.04. This is word embedding, this is positional embedding. We have to add both of them. So the addition of word embedding plus positional embedding will be 0.11, 0.22, 0.33, 0.44. So for every token, vocab, whatever you want to say, these two are done and added. Your step number one is over for the encoder. Okay, right now I am dealing with only encoder block. So input embedding, addition of positional embedding, over. This you are going to give as an input to multi-attention head here. You will make a residual path also. This is a residual path. You are tapping this input via path so that again give it back to the output which is produced by the multi-head attention. This is called as residual path. I have seen residual in computer vision pre-trained model. The name is residual net, ResNet. If you have heard this name, ResNet. The task of residual is to preserve from exploding gradient descent or vanishing gradient descent. Okay, so this is your residual connection, EA. Fine. So what will happen? You do have so many tokens. Every token embedding will be done. Okay. This embedding will be taken as via residual path. Also, it will pass through three linear layers. Three linear layer. Layer 1, layer 2, layer 3. It got split by three linear layer. These layers itself called as Q, K, V. Linear layer means something which perform Wx plus B. Okay. I will give some mathematical forms also. So QKV are three linear layers by which your input gets splitted. And we are going to get query, key, and value. Rest you know what happens with Q, K, and V. You are having, let us suppose, V1, V2, V3, V4. The embeddings for I am very happy. So these are the vectors, these are the embeddings for the words. Let us suppose query be V1 or word I. Then you know the first step of attention, that is called as self attention. Here they are writing multi head attention. Head means self attention. Multi head means multiple self attention. Okay, so you will be having many self attention mechanism present. So your data input is divided into n parts, and it will be supplied to all self attention. That's why it is calling as multi head. So what happened in a self attention that we already studied multiple times, various times. Step number 1 is q dot k. Okay, that means you have to take the dot product of query and the key. That is v1 dot v1 v2 v3 v4. That's what you have to take, the dot product. The result will be, okay, that's w11 w12 w13 w14. These are attention scores. Okay, these are attention score. So if you make a representation like a matrix format, we can say I am very happy. I am very happy. So what you calculated now? That was this line W11, W12, W13, W14. That's what you have calculated. Same you have to calculate for M, where you are going to take it as V2, V1, V3, V4, V1, V2, V3, V4. So I just calculated this thing. Next will be W21, W22, W23, W24. So once you got these attention scores, the next step is to scale them. Scaling. For scaling, you have to give this entire matrix and divide it by under root of dk, where d is the dimension, key dimension of key. That is k. Okay, so that's what you have to take. Under root of dk.
Sir, what is this dimension?
What is the key here?
Okay.
This is 1 cross 4 I am taking now.
Class 4.
So let
Okay.
us say 4. Okay. Let us say 4. So square root of 4, that will be 2. So divide each and every value by 2. That is scaling. So here you have to give this entire matrix of attention score, and you will be getting scaled attention score. Next, you have to give the scaled attention score to softmax activation function to find probability attention score. This is probability attention score. That means the values now in that matrix will be between 0 to 1. All the values between 0 to 1. Okay. And softmax is given as, the formula for softmax is e key power xi divided by summation of e key power xi, where xi is your attention score, which is filled in the matrix. okay, which is filled in the matrix. You are having a 4 cross 4 matrix. So whatever be the values filled inside it, that's what you have to take as X. Okay, got it. So this is the result which you are going to get from Q dot K. Fine. After that, means after this step, that means you performed, you got some result, attention score, you perform scaling, you perform sort max, and then you got something that is the attention score. You have to multiply this attention score with value, and value is same. That is your V1, V2, V3, V4. That's the value. So multiply this attention score with the value. This is the final step of attention mechanism. You will get some output. This is the final step of attention mechanism. Now get back to architecture again. So if you are seeing here three arrows, it means QKV. N cross means you are having N self attention. That's why it means multi head. Okay. Whatever you are going to get from this multi head, you will be having self attention 1, it will give some output. Self attention 2, it will give some output. Self attention 3, it will give some output. Self attention n, it will give some output. You have to concatenate all. Okay. So the next thing is concatenation. This output is of a self attention. There will be many self attention. Whatever be the results you are getting, concat. And also, you can see you have a residual connection also. So this positional embedding along with the word embedding which you have got from the first step, add this also. Add that WE plus PE also that you have achieved. And whatever be the result you are getting here, you have to perform normalization of it. Normalization. So normalization is a layer. That's a normalization layer. Again, we are picking each and every point in normalization to convert it into some standard form. Normalization. The word normalization always reminds me that we are trying to make the distribution normal. That's what we are trying. We are having the values of the vectors which are continuous in nature. Normalization, because I picked this thing, normalization, it's present in the architecture. So we are trying to have some kind of such distribution. Normalization, we are having standard scalar also, standardization, which says that this is the formula. So we are transforming our value into such notation. Again, the reason is when we are going to perform the training and gradients calculation will be done, we don't want gradients to be vanish or neither explode. So keep the values in a particular range so that it will be easier for us to calculate the gradients. Fine. So I want to give you some tips here, that let us suppose your input x is of n cross d. D is the dimension of model, n is the sequence length, this is sequence length, and d is the model dimension. In transformer we do tokenize, and we have a number of tokens, actually number of tokens to process. That will be like, okay, 3000 tokens or 4000 tokens, which is far more than your previous ones r and n. And its relatives like LSTM by LSTM, they are having very small sequence, short size. But in case of transformer, we are having advantage, we are having big length of the tokens. Also, transformer is parallel. It can perform parallel processing. In these, I can't perform parallel processing. That's a drawback. In traditional architectures, we can't do that. Transformer, we can perform parallel processing. So right now, let us suppose this is your sequence, this is your input, and n is the length of the sequence, and d is the dimension of the model. Okay. So your q, k, and v are having input, that is your after. Okay, what is this input? After you're embedding, you're getting this input x, that is of like a real number with this particular, it belongs to this particular length. Okay, so x into wq, k is equal to x into wk, and value will be x into wv. So here wq, wk, and wv are weights. These are the weights. Okay, and the weight wq belongs to r dimension of model multiply by dk, that is the dimension of key. Wk also belongs to R dimension of model into dimension of key, and Wv belongs to R dimension of model into dimension of value. Okay, so we are having these q, k, v. X you have to multiply with the weight, then you are going to get the q. What will be this vector or a matrix will be? What dimension this vector or matrix comprises of? This is what you are going to get after the operation, after this operation. And if you ask me, sir, you are writing d dimension of model, you are writing this dimension of model. So let us suppose if your model dimension is the input dimension. input dimension. Model dimension is input dimension. Okay, you do create a model, na? You do create a model. Model dot add dense 512 activation function relu. You create, na? You create a layer, na? So what is this 512? This is the dimension. You are having a layer with 512 neurons present in it. It is saying that only. Input. That's an input dimension. Okay. So, okay, here this is your input sequence multiplied by the dimension of a model. For example, I do have a sequence length 2, n equal to 2. N equal to 2, let us suppose. So 2 into 512, the 1024, that is your input. Input is 1024. Okay, so here you are having 1024. Okay, from 0 to 123, 1023, and this is your 512. Okay, like this you can prepare. Okay, and we have to split this 1024. This 1024 needs to be splitted to give to QKV. So the value of Q will be x into w to the power q, x into w to the power k, x into w to the power v. To the power v, it's a subscript actually, not super. It's a subscript. Just consider below. Okay, I just already mentioned. Fine. So if you want to let me correct this thing, so it's like this: Q K O V. And I've already mentioned what is WQ. What is the dimension of WQ? Okay, the dimension of WQ is this thing: dimension of model into DK, and these are the dimensions. Okay, fine.
Sir, what is R?
R is a real number. That
Okay,
means
okay.
this belongs to a real number. Okay, we do write in our set theory and all this ना ये इसका वो है रिप्रेजेंटेशन है. ओके,
Okay.
फाइन. तो ऐसा आपको मिलेगा. ठीक है. और ये जो वेट मैट्रिक्स है WQ WK WV, यही प्रोजेक्ट करेंगी. दीज प्रोजेक्ट द इनपुट, दीज प्रोजेक्ट द इनपुट over Q, K, and V layers. These project. Okay. And ये attention mechanism का task over हुआ. You perform Q dot K and everything you perform. Then also I taught you here. I also taught you here that we are having residual connection. Okay. So ये यहाँ पर वापस टैप करा. Concatenation of all these self attention I did. I added this part also and performed normalization. After normalization, the result which I got, again I will be performing a residual connection. ये residual है. This is again a residual. And फिर ये जो रिजल्ट आई हैव गिवन टू द फीड फॉरवर्ड नेटवर्क. ठीक है, फीड फॉरवर्ड को दे दिया मैंने. तो रेसिडुअल कनेक्शन व्हाट इट डू, वट एवर बी द प्रीवियस आउटपुट, I am again tapping it back to the current layer output. Just the thing is vanishing gradient problem. Okay, we don't want to get trapped in vanishing gradient problem. That's the reason I'm tapping it back. Here in feed forward, it operates your feed forward, that is step number 3. Feed forward operates independently on each token. Okay, it operates independently on each token. And it's same for all the tokens. Okay, in feed forward, you are having two linear layer, L1 and L2. You are having two linear layers in feed forward. Okay, and I already told you what the linear layer do. Wx plus p. This also perform Wx plus p. So this will be the feed forward network. You are having linear layer 1, you are having linear layer 2. They are connected by ReLU activation function. ReLU or JELU? Either ReLU, either JELU. We know about ReLU. So ReLU activation function. So whatever you got from multi-head will be given to here. Okay, and this operation is performed Wx plus b. Input into weight plus bias. Okay, now one more thing. In this particular case, L1 L1 converts L1 converts your input, that means the which I am going to get from the multi-head, into high dimensional data, high dimension data. And L2, what I am going to get again, this high dimension data, I give it to L2. L2 again convert this high dimensional data in original dimension. Okay, that's what L2 do. So these are the layers which will be having the neurons, and it is pointwise. This is pointwise feed forward. Why pointwise? I already told now that feed forward do take care of each token, token by token. Okay, it operates independently on each token in a sequence, and it is same for all the tokens. And the goal of this feed forward, why we make deep learning model? To identify complex pattern in data, complex pattern in data. That's what we are doing here. Same thing, to identify complex pattern in the data. Okay, so after performing this task, feed forward, we whatever be the result we are going to get from the feed forward, add the result which we have got from the previous layer. Okay, so the result from here and the result from the previous layer, just add both of them and perform normalization again. Normalization. Okay, this is what we done with the encoder. So now we are having attention data. Okay, fine. So we got importance of each and every token, what we have given as an input. Then starts the decoder. In decoder, we are having five components. Again, first one is positional encoder. Second one is mask multi-head attention. Then we are having multi-head attention, that is of encoder decoder. That means the input which I got from encoder will be given to this second one, and it's multi-head of decoder. So I am saying multi-head encoder decoder. This is mask and this is multi-head attention encoder decoder. So this is your first multi-head, this is your second multi-head. Two multi-head we are having in decoder. Then we are having the feed forward as usual, and then we are having a linear layer where we are available with sortmax function. That's it, five components. Now, as the question asks, as I already told, though your transformer is trained on a huge amount of data, so it is having a knowledge what to produce. Decoder have some knowledge that what could be the output of a particular input. However, in general we say that decoder do not know the output sequence in advance while making prediction. Just note this line: decoder do not have decoder do not have the output sequence in advance what it needs to predict. Don't what to produce, what to predict. But why I said in just few seconds prior, what I said, decoder has a knowledge, decoder has a knowledge from its training. During training it knows the ground truth, what could be the output, what could be the output, but not exactly that this will be the output. So we are just बीच का रास्ता निकालने की भी बात कर रहा हूं मैं. ट्रेनिंग से तो भाई वो सब जानता है, उसकी ट्रेनिंग हुई ना ह्यूज अमाउंट ऑफ डेटा पे. माई ट्रांसफॉर्मर दिस एनकोडर डिकोडर इट्स बिन ट्रेन ऑन ह्यूज अमाउंट ऑफ डेटा. तो ट्रेनिंग के हिसाब से तो इट अंडरस्टैंड्स कि ग्राउंड ट्रूथ क्या होगा, आउटपुट क्या होना चाहिए, वो समझता है इस बात को. लेकिन फिलहाल उससे हम प्रिडिक्शन करवाएंगे. यानी कि डिकोडर जो उसने सीखा है उस इंफॉर्मेशन को यूज करेगा. यूज द इंफॉर्मेशन ऑफ ट्रेनिंग. और भाई ये ऐसा है, आई एम टीचिंग टू यू ऑल, आई एम ट्रेनिंग टू यू ऑल. You know, if I ask you, define transformer. Because I am training you, because I am teaching you, so you know you are having an idea about this thing. But I will ask you to write in a question paper. तो डिकोडर से प्रिडिक्शन करवाना वो क्वेश्चन पेपर वाला हिसाब किताब है. बाकी पढ़ाई तो करी ना भाई इसने. आप मेरी बात समझ रहे हो मैं क्या कहना चाह रहा हूं? आर यू अंडरस्टैंडिंग इट और नॉट? तो डिकोडर जानता तो है, उसको पढ़ाया है ना मैंने. अब फिर मैंने उससे सवाल करा कि भाई द कैट सैट ऑन द मैट, इसका तू फ्रेंच ट्रांसलेशन कर. अब मैंने उसको इंग्लिश टू फ्रेंच पढ़ाया है, वो जानता है. ठीक है. इसी कंटेक्स्ट में ओके, इसी कंटेक्स्ट में हमने यहां पर उसको डिकोडर में वी गेव इनपुट, फ्रेंच एज एन इनपुट. Okay, French as an input. A information. That means decoder is using prior information. Okay, decoder is using prior information. Okay, decoder is using prior information. What it has learned, what it has done during training. सो इफ यू आर सीइंग सर, डिकोडर में आपने आउटपुट तो पहले से ही दे दिया था ना, ये डिस्कशन हुआ था ना हमारा, वो कर रहा था ना ला शेन वगैरह, तो भाई ये इंफॉर्मेशन है जो उसने पहले सीखी है. ठीक है, तो इस इंफॉर्मेशन का, ये ला शेन, अगेन द सेम पर्सपेक्टिव, पोजिशनल एनकोडिंग होगा. फाइन, दैट मीन्स अगेन दिस बी एज अ टेक्स्ट, टोकन, vocab, एम्बेडिंग. एम्बेडिंग में वर्ड एम्बेडिंग, पोजिशनल एम्बेडिंग, बोथ ऐड करो, सेम यही होगा. तो ये इंफॉर्मेशन है जो उसने ट्रेनिंग में, उसके दिमाग में आएगी ना यार. अच्छा, आपसे भी कोई सवाल पूछते हैं तो आपके दिमाग में आता है कि नहीं आता है कि यार ये पढ़ाया था, क्यों भाई सही बोल रहे हैं आप, लॉजिक समझ रहे हो मैं क्या बताना चाह रहा हूँ.
Yes, yes, sir.
बस ये वही
Yes.
उसके दिमाग में आया. ठीक है, अब इसके बाद द नेक्स्ट थिंग इज, इसकी सेम एनकोडिंग हो गई. नाउ वी परफॉर्म मास्क. ठीक है, नाउ विल परफॉर्म मास्क मल्टी हेड अटेंशन. तो ये जो एम्बेडिंग हुई अभी कंप्लीट, उसका वो यही मैट्रिक्स बनाएगा जैसे बनाता था. ओके, इट विल क्रिएट द सेम मैट्रिक्स. सो ले शेन एंड वॉट एवर, ले शेन वॉट एवर, उसकी वो अगेन इट विल परफॉर्म, इसके अटेंशन स्कोर्स निकालेगा, इट विल कैलकुलेट द अटेंशन स्कोर्स, it will perform the scaling of it, it will perform the sort max of it. ठीक है, वो करेगा, सब कुछ करेगा, एंड वो इसका ये सब कर देगा. एंड देन ये करने के बाद स्केलिंग करेगा, शॉर्ट मैक्स करेगा, उसके बाद यू आर गोइंग टू ऐड मास्क मैट्रिक्स. वो इन्फिनिटी वाली याद है ना आपको, इतने दिन से पढ़ा रहा हूं. ठीक है, वो इन्फिनिटी, माइनस इन्फिनिटी, माइनस इन्फिनिटी, माइनस इन्फिनिटी, माइनस इन्फिनिटी, माइनस इन्फिनिटी, माइनस इन्फिनिटी, जीरो 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 जीरो, वो इसमें ऐड कर देगा. ठीक है, इसको स्केल करके शॉर्ट मैक्स करके, भैया वी से मल्टीप्लाई मत करना, अभी वी से नहीं करना है, वो बाद में करेंगे. ठीक है, जस्ट गिव इट टू मास्क मैट्रिक्स. मास्क में देने के बाद जो रिजल्ट आएगा, यू विल बी गेटिंग ऑल दीज एज इंफिनिटी. ये सब इन्फिनिटी हो जाएंगे, ये वाली वैल्यूज रहेंगी, द वैल्यू विल बी प्रेजेंट. मुझे ऐसे ही लग रहा है. और फिर ये जो आया है, अगेन यू हैव टू गिव इट टू द शॉर्ट मैक्स, सो दैट वो वैल्यूज जो इन्फिनिटी वाली है वो जीरो में कन्वर्ट हो जाएंगी. दैट ऑल्सो यू हैव सीन, दोज वैल्यूज विल कन्वर्ट इनटू जीरो. उसके बाद भाई इसको वी से मल्टीप्लाई करना, आफ्टर दैट, नॉट प्रायर. ये आपका रिजल्ट आएगा मास्क मल्टी हेड अटेंशन से, ये रिजल्ट आएगा. गॉट इट. सो हम डिकोडर के यहां पर आ गए हैं. ठीक है, सो आपने पोजिशनल एम्बेडिंग कर ली, मास्क कर लिया. अगेन आप ये यहां से रेसिडुअल नेटवर्क यू आर अगेन यूजिंग, दिस इज रेसिडुअल, यू आर यूजिंग दिस थिंग. ठीक है, रेसिडुअल लगाइए यहां पर, कॉन्कैटिनेट करिए, रिजल्ट्स को ऐड करिए, वही रेसिडुअल से पोजिशनल एनकोडिंग ऐड करिए, नॉर्मलाइज करिए, एंड देखा ना क्यू के वी तो यहां भी था. एंड फिर उसके बाद जो रिजल्ट आया, द रिजल्ट विच यू गॉट, ये इसको मल्टी हेड अटेंशन में दे दीजिए. ओके, मल्टी हेड में एनकोडर का भी आएगा, वहां पर होगा द कैट सैट ऑन मैट, ये होगा। यहां से आपको वो ली चैन वगैरह आएगा। तो मल्टी हेड में भाई इन दोनों का यू हैव टू कंसिडर दीज टू, ऐसे ये करना है आपको, ठीक है। द कैट सैट ऑन मैट, ठीक है। और ऊपर क्या लिखोगे, ली चैन डैश जो भी होता है वो लिखोगे, ठीक है। तो ये ली का सबके साथ, तो मेरे हिसाब से ये इसको इधर, चलो कोई बात नहीं, अटेंशन स्कोर्स, ली का सबके साथ अटेंशन स्कोर आएंगे। उसके इंग्लिश वाले आएंगे, इसे आपको स्टैंडर्डाइज करना है, शॉर्ट मैक्स करना है, दैट विल बी योर द रिजल्ट। देन फिर आपको डॉट प्रोडक्ट करना है वी के साथ, दैट विल बी द रिजल्ट। सो सिमिलरली जैसे ली का है वैसे हर एक वर्ड का होगा, फॉर एवरी वर्ड that I have explained you in the previous class. So this will be the output which will be produced by attention mechanism present here. Again, add करना है, normalize करना है, same thing. So this is what you are going to get from the multi-head attention, and the explanation, okay, जो अभी मैंने आपको दिया, that is present in that article also which I have shared. उसमें दे रखा है, आप पता करेंगे द का ली, फिर द का कैट, फिर द का सैट एंड इसके साथ। तो हर एक फ्रेंच वर्ड का उसके इंग्लिश का ऐसा आपको करना है, एंड दैट्स व्हाट यू आर गोइंग टू गेट। फीड फॉरवर्ड और ये पूरा वही की वही है जो अभी समझा चुका हूं एनकोडर का, सेम, this entire is same what I explained in the encoder. And the result which I get from this will be given to the linear layer where I am having shortmax activation function. Shortmax activation function will give you the probability that which word will be the next word. तो यहां पर हमने जो गेम करा है वो ये है मास्किंग वाला। ओके, तो decoder is using prior information what it has learned, but by doing the masking we are not intimating it that this will be the future word. So masking करने से उसको future word नहीं पता चलेगा, तो वो चीटिंग नहीं कर पाएगा, चीटिंग वो नहीं कर पाएगा। उसके दिमाग में तो बहुत सारी बातें हैं लेकिन हमने उन्हें हाइड कर दिया। वी वांट कि तुम प्रिडिक्ट करो, समझ गए मेरी बात? यहां पर प्रिडिक्शन एक्सपेक्ट कर रहे हैं उससे, यू प्रिडिक्ट फ्रॉम योर साइड, गॉट इट और नॉट? This is the final output from the decoder. That's how encoder decoder work. Okay, so I have sorted out this architecture. This is the architecture of transformer, this is the architecture of encoder, and this is the architecture of decoder. This also I will share with you. This is the entire working. Okay, next class में एक terminology और बता दूंगा. Okay, let me stop presenting. Let me stop recording.